Hi, this video clip is about a missing week 10 lecture of ELE336 Microprocessor Architecture and Programming at Hacettepe University, and about to explore some details related to ROM and RAM interfacing, simultaneous interfacing, and their technical properties are not exactly the same. For example, assume we are given a design that could be a very simplistic design, not state-of-art technique, but compatible with our existing microprocessors and RAM and EPROM, etc., memory banks, and it's actually synthesizing both ROM interfacing as well as RAM interfacing together. So designing a microprocessor system, actually that's a very basic primitive motherboard that accommodates one 16K by 8 RAM and one 1K by 8 ROM. And the starting addresses for RAM is given 10000 physical address in hex, and ROM starting address is 42000 hex. There is no special magic reasons for selecting these numbers. Those were just copied from very old textbooks examples at that time. So if you learn to connect to these addresses by selecting appropriate addresses, you can define any arbitrary address in the memory map of 1 megabyte memory map of x86. And other constraints are to use the minimum hardware for cost and decoder or any other interlogic circuit selection for simplicity or convenience. Now, in order to start the solution, first we have to visualize everything in a block schematics concept. As we remember from the lecture notes 2 weeks ago, the RAM has 14 address pins, 8 data bus connections, and 1 enable input. Similarly, from the same week, our ROM is or consists of 10 address bits and 8 data pins to be connected to the board system, and their realization and the reasons for these number of pins are given underneath the images. So basically, actually, we are connecting address bus and data bus coming from the microprocessor. Also, microprocessor is connected to these buses through latches. So these 5 groups of nibbles for terminals represent the 20-bit address line bus of our motherboard. And now RAM is placed at the right side of it, and the starting address of the RAM is given above the circuit element, and we will be utilizing the rightmost 14 bits for the RAM internal addressing and remaining 6 bits for addressing. So, or enabling the RAM. So enabling the RAM basically is a process of setting the enable active low output to 0 state when certain combination of address pins starting from A19 and finishing at A14 comes. We want to have 001, sorry, 000 and 1 for the first nibble and 00. So we have actually 6 digital inputs to enable RAM. The others should be high if we want to use a 13 input NAND 74133. So that circuit definitely works fine, but it requires at least 2 integrated circuits, 74133 and 5 inverters. So these inverters are 7408 or similar. So this is our first choice of NAND gate to address decoding to enable the RAM, as given in the previous diagram. There is a better choice. Instead of two logic integrated circuits, we can utilize only one 3 to 8 decoders, 138, which had already been explained in 2 weeks ago. So according to this configuration, we can assign to the address buses and only at a certain combination of starting from A19 low, A18 low, A17 low, A16 high, and A14 and 15 low, only Y0 output initiates a low signal to enable the RAM. So this is one chip more economical compared to the previous one. This also works. So as a result, utilizing decoder is cost effective, as well as on the motherboard, less space and less engineering labor is required for this certain particular example. In the second step, the ROM connection is realized. The principle is exactly the same. The only difference is from the 20-bit address line, the first or rightmost 10 bits are used for ROM internal addressing, and the remaining 10 bits are used for enable. So there should be a connection that we should make for this certain combination of 420 hex. The enable should be low, and this can also be realized by one, big NAND gate with this combination. With the address pins, requires lots of inverters, 2 chips for inverters and 1 chip for the big NAND gate. So it requires 3 integrated circuit or combination logic circuits to enable. Similarly, if we use 74-138, 2 of them, 3 by 8 decoders, 2 of them, please study these connections so well to understand the rationale. The first 6 bits control the first decoder, and this decoder enables low signal to enable the second decoder. So if 6 bits are okay, then the second decoder will be enabled. It will receive another bits, well, less number than 6 bits to enable. So in the same Y0 output, because A, B, C of the second bit receives low signal, then the ROM could be enabled and it will work. And according to the address information from A9 to A0, which is 10 bits, the ROM internal addressing will be complete so that the data can be outputted to the data bus. So this is, instead of 3 chips, we use 2 chips for decoding or the control logic for this. So our overall solution, okay, in this, let's say, partly represented schematics, the physical address bus is shown with 20 bits in the middle. Microprocessor and associated latches are not shown. And other control circuitry like clocks or other stuff, again, are missing and neglected. Our RAM and ROM are shown with the associated control circuitry. Now, as a cumulative representation, you see 3 decoders for 2 memory components, and the output of these both memory components are connected to the data bus. Well, of course, data bus can be directly connected because some RAMs or ROMs have output enable or internal latches. If any RAM or ROM has a 3-state internal latch, you can connect their outputs directly. But if not, you have to have external latches or bus transceivers. If this is a RAM, so two-way data transfer could be possible by another extra control. But usually output enabled pin exists for these RAMs, so that data bus connection is in 3-state condition. This is the circuit schematics drawn with the professional software to draw certain electronic or logic circuits. The same circuit with a conventional, more professional look, and this blue upper thick wire represents the data bus, and this vertical wire partly represents the address bus, where due to some coloring or transformation mistakes, some of the connections are not shown directly, but believe me, you connect the address bus connections to the address bus accordingly, and the address bus lines for the decoder starting from A19 up to A10 are given underneath. And these are the two chips for the RAM and ROM connections. Now I will give a self-exercise for you. Even in the final situation, instead of utilizing 3 decoders, you can use 2 decoders. That could be a more smarter approach. So one combination, one of the output pins of the decoder would be active low to activate RAM or ROM, and for another combination, the other. So there's a possibility of you can even decrease the number of decoders to 2. So that could be given as a homework. So this is the moment that our first motherboard would have been designed in our lecture, and you can also design, let's say, very similar motherboard by using an 8-chip CPU, 8088. So this is a simpler one than 8086. And our motherboard consists of our microprocessor, memory bank from 2 very basic or primitive memory elements, and some number of I/O ports. So that would be our basic motherboard design. Our ROM and RAM are exactly the same as previous 1 kilobyte by 8 and 16 kilobyte by 8 memory elements used in the previous lectures or parts of the lecture explanation right now, or lecture movie. And 8 ports, each having 8 bits width. Okay, so total 64 pin output ports could be possible, and this was also shown in the last week by introducing the 8255 and, let's say, 64-bit output port examples in the week number 9 of the lecture material. So if you look through these specifications, this is the connection of our microprocessor and associated latch. This microprocessor has 8 data output pins, so it's not 16 output data pin kind of microprocessor. It's simpler than 8086. It has 20 physical address pins as usual, and address and data bus are multiplexed so that one latch is definitely, at least one latch is required to latch the 8-bit, the first least, the rightmost 8-bit address, and it's connected to the data bus. So whenever address latch enables signal enables this latch, the information content of this AD0 to AD7 means that it's an address information, it's directly sent to the output port. And there is no latch to connect to the data bus, except that transceiver, which could be necessary later on. The same 8-bit information of AD0 to AD7 also may represent data out when address latch enable signal does not enable the address latch. And moreover, some control signals related to input output, reading and writing, and memory, we have seen in the week number 9, previous week, that 3 signals from the microprocessor are converted to 4 memory read, memory write, or input output device read, input output device write signals, 4 active low signals to enable the related ports. And their bus timing signal diagrams are also shown. We will not cover this in detail, but this was presented in week number 9 about the cycles of the clock to enable the signal, okay, write the data, or the data is ready, signal present. So basically, the clock or the period machine cycle is completed after 4 clock periods. So this, okay, this is, again, this is left as an exercise. Our previous 8086 or 16-bit microprocessor and memory interface can also be implemented by utilizing 8088, which is an 8-bit version. The only thing is you have to be careful about, you should not use 16 bits for data, and only 8 pins of the address and data are multiplexed, and the other connections are much the same, identical to the 8086. So now you have an ability to design a full motherboard for very simple 8 and 16-bit microprocessor and associated simple memory and input-output devices as well. There are some solved examples. I will go through them in a basic, let's say, or critical points of overview, and these are left as a self-exercise for you. For example, these examples are mostly includes both assembly codes and their hardware part effects or implementations. So for example, from any pin, you can connect a LED. Connection LED is not direct. You have to connect a resistance as well. And you have to turn on the LED for some time and turn it off again for some time, or turn it on and off by oscillating region with some milliseconds or so, seconds delays or kind of things. You can do those kind of things with both assembly and hardware all together. For example, assume the address is defined for the LEDs like this. You send some data to this address, makes corresponding bit for the LED to be on if that signal is high, for example. And since the microprocessor is so fast, you should want that this on condition should be or should sustain for some number of half seconds or 1 second, so that you can see it, a human eye can see it. So you have to write some assembly routines to have some kind of delays for visibility. If you turn this LED off, again, you should again define or add this delay to the program so that you can follow the on and off, let's say, toggles of these LEDs, etc. And you had to design, control, enabling schemes and logic circuits for the address selection. It's the same as week number 8 materials. 8255 or simple I/O port additions utilizes the same thing. So grab that information from there to apply it to a single LED, turning on off and on for this particular example. Actually, this question is related to flipping a bit at the output, which is an address, controlled by our microprocessor. Specifically, we have to write a code to flip D0 and D4 bits, for example, for 2 LEDs at the output at this address. How can we do that? First of all, you can analyze this assembly code very easily, so I will not repeat the same thing. You had done it for many weeks before the hardware things. And there are some 3 stars, so these are self-exercises. If we set any LED on, how can we create a command to set it off? There are many solutions for this question. We can write some data and then send this data with ones once again, and then zeros. I said this is one solution. Or you can do bitwise logical operations on the bits like XORs or so, because they can also give 0 result or any desired result. You cannot end directly because ending with something gives always the same thing, so you cannot flip. So you have to find some kind of logical operation so that there should be a toggling action, ending and rather than ending and ORing with a fixed number. So the same thing or the correct solution for this exercise is XORing the AL for the data to be sent for the LEDs with this binary information where X stands for don't care any information for that particular bit position is all right, either 0 and 1, but the fourth or bit 4, bit 0 should be all 1. So XORing the same thing will give 0 and different thing will give to 1. So it will be a toggling action. In another question example, what's the stack pointer and 8-bit content of the stack location? The end of code is reached. So it's very typical for only assembly code exercises. You can now, I mean, I will not go through this because this is not related to the hardware. You follow all the codes. You have to write the results by pen and pencil and eraser on a paper, then find the solution. The best thing is run the same code in M8086 and then compare the results with your solution like this one, and then you can learn and implement by yourself very well, and you don't forget it for a long time. So this is the verification moment of the previous codes. I suggest you do the same thing by your, during your own studies. This is another question. Again, this is a sample question to, let's say, prepare yourself to test your progress with the material. This is again an assembly code creation and away from the hardware part. So I will only mention a few things about the method that you should follow for your own improvement. So this is an assembly language design process. You find suitable assembly codes to be run by x86, and MDB is the label for data location and this is an, let's say, unknown number of data kind of approach. And in the main program, there are some constraints, and finding the average and subprograms, etc., very similar to the temperature averages that we had gone through in the week number 5 and 6. So this program is again creating an assembly language. Of course, I suggest you also draw flowcharts, because from flowcharts to assembly code, you can transfer or find the assembly code very easily. And finally, you test the algorithm by using the assembly code. So these kind of flowcharts are very valuable. Then you connect, and you can find your own mistakes in a very, very easy way. So that's left as an exercise as well. You can. So this is the final stage of final calculations to find the average, etc. These error messages, etc., are critical. Those are exceptions. For example, sometimes unknown or undesired values may be given. The program may give a divide by 0 error, whatever. So in those exceptions, your program should handle. That's the reason many computer programs fail today, because of the lack of defining those kind of exceptions. So exceptional routines should be handled. In all parts of the program, you have to check your data there. Are they within a specific limit? Are they negative, positive, non-zero, whatever? Those constraints should be checked during the program as well. So that was the general philosophy to write any assembly code, any computer program. Oh, that's about it. So now, if we summarize, this week was about to explore the details of designing your first motherboard, including your microprocessors of this semester, and giving 3 big examples of fully designing assembly codes, and one example is fully related to both assembly code writing and manipulation or implementing the desired result by LED blinking at the outputs. Thanks for joining that online session. Actually, this is offline education slides, and hope you had benefited it. And give me a feedback for anything related to week, and wishing you health and success. See you in my next meeting.